Welcome to another video on Triton programming language. Today we'll look at reduction algorithms. So, reduction algorithms, for example, are let's say you have a matrix and you're doing row-wise summation. So, where the dimensionality of your input changes. So, let's say you have an m by n matrix and you take sum over the columns. So, uh, all the columns get into a single number, right? So, from a m by n you get a m dimensional row matrix. So these type of operations, or another example could be finding max over the columns. So you have an m by n matrix and then you find the max over columns, right? So for m by n then it becomes m. So you are right here we are doing columns, or we are doing max over the columns, right? Similarly you can do it over rows. So let's see how do we do these type of mathematical operations in Triton. So this is an example. Let's say you have a matrix which has m rows and n columns. So here, what we are going to do is for each row, each of your program ID will be. So we are going to tile the basically we're going to tile it over rows. So for each row, you'll have to calculate the max or sum. So let's start with a simple sum example. The first one is row-wise sum. So for each row, you find you sum all the columns for that row. And so, for example, you have a matrix m by n, and for row zero, you'll take the sum of all the columns for row zero. That means, and also let's say your because your column can be of any dimension. It's a huge number, so we do it in blocks. So here first you'll find the sum of this, then you'll add that to sum of this, right? So you can divide all the columns into block of n and then calculate the sum for each block, and then you'll have a running accumulator and add it over. Then once you get the output, so uh, your output of row zero will go to out of zero, right? And then you do sum of all is the columns here, right? That's the whole concept. So for each row you'll have a program ID. So we have m rows and n columns, so you'll have program. So each row will be done in parallel. That's the whole concept right here. Okay, so because if we have m rows, each row is being done in parallel, it's going to reduce significantly your speed, right? This is what Triton allows you to do on GPU. Let's see how it is done. Yeah, but overall, we'll be doing this in today's video. Reduction algorithms. Let's look at the summation, and then we'll do max and softmax. Right. So for each row, you're basically parallelizing on the row dimensionality. You will have m rows, and all of these, each row will run in parallel, and for each row you will have to sum all the columns. Okay, so I'm importing Torch here. I'm importing Triton, and then Triton languages TL, and this is the core kernel. Okay. So I take input pointer x and then output pointer, and the output pointer will have only one dimensionality. Your input pointer is a matrix here, and then m is the number of rows and n columns, and then stride of xm is how much, like what is the jump from going from one row to another. That's your stride. And then you have stride xn, which is what is the jump to go to another column. And block n, as I told you, instead of summing all the columns at once, we do it in block. We take block n columns and then block, right? So one by one block n columns. That's how we add. And that's you. That is what you can define this. This is a variable. Okay, so here we are. You since we are doing it over rows, you have to do program ID zero. So zero is your one dimensional on the row axis, right? So you get a program ID. Each program instant handles one row. Then for that row you have to find the offsets, right? For each, like how do you want to go column wise. This is you do 0 to block of n, that's you get the column offset. This instance will load. So offset of n is 0 to block n. We are doing it in block n, and you'll see how this. So then row start is you multiply PID with the stride of x. So uh, because you need to find out, this is your base pointer, each program instance where you are in your overall, right? So x pointer is your global, but within that global pointer you need to actually jump to the exact row, right? And in memory everything is stored in one dimensional, so you need to find the exact place where your pointer should point to. So row start is basically take the PID of this particular kernel, like this particular program ID, and multiply it with a stride of xm. So you get the road. Now I'm defining, this is how you, I'm defining an output like a running sort of accumulator and calling it zeros. This is just a scalar. So this is starts with zero and then it's of the float type 32. So this is just a, like you would like just a variable which is have it has a value zero, and then you start the loop. As I told you, we'll be processing each the columns in block n chunks. So you do 0 to n, right? Because we have n columns and then block of n. You go, so each time you take you process block n, okay, and then your you have, once you have this, you get the offset. You take your base point, like the first number that you had from here to here, and you add it to n, because you have to go in blocks of n, and then you make sure you're not out of bounds with by calculating mask. And so yeah, and then you actually load your input number, the values. So what you do is you've taken your base pointer, to that you've added the row start, right, which row you are in, and then the this offset that you get, okay. So multiplied with stride of xn. So this will load the actual values, and then mask is to make sure that you don't go out of bound, okay. So once you get x, you find the sum. This will be certain blocks of rows, then you find the sum of that. So I'm doing TL sum x, and along the axis 0. So you this is a running loop. You have you're initializing this outside the loop, and then you go on adding, summing each value to it, right? Once you're done with this, you'll get the sum of all the columns for that particular row, right, wherever this PID is. So all of these are running in parallel, so you basically will get the sum of each row, and then you store that. But yeah, we have the output pointer, and we store the accumulated value in this pointer here, right? So you do out pointer, and then the stride of, again, the output needs to be, has the will have the same dimensionality along them as your input is, right? And then you add PIDM here. PIDM will be 0, 1, 2, 3 all the way till m, right? Yeah, and you add that. So first, for the zeroth row, you'll have output pointer, and you'll just put it there, because output pointer plus 0 is that. And then for the next PID, when this increments to 1, you will have output pointer plus 1, and you add it. So this runs. This is how you'll calculate row m. Now, to run this kernel, here is like the launcher. I have the I have the input x that comes in, right? I get m rows and n columns, and then output has to be of the same shape as m. So I'm doing empty m, right? Device, and both, all of that has to match. And then this block n depends on, you have taken 128, but yeah, it can be any value. And then you launch the kernel, right? And here, when I'm launching the kernel, this is a one-dimensional kernel I'm launching along the row axis. So I've given m, there is nothing here, right? It's an empty one element tuple. And then I pass in all the values. X is the input, and then output pointer, m, and stride of x in this thing, and then the whole block. And once it's launched, and then I return the output. Yeah, so let's run this. Similarly, I'm just calling this function here. I'm initializing a random matrix of 512 by 1024, and then this running it here. I'm running it using torch, right? And then comparing it torch, and what is the output that I get using my Triton kernel, right? So yeah, ref, and then out, and then making sure that there is, like, it's almost zero, okay. The difference, absolute difference, should be as low as possible, okay. Yeah, so I run it, and then you actually see that if you do it normally using torch, and then using our Triton kernel, it's the same thing, uh, and there is no difference. So that means our kernel is correct theoretically, all right, because this is zero and both of them. And but yeah, the difference is, if you run it, you will realize how fast this is, right? So we ran it, and like, if you see here, it just ran so quickly for such a huge and matrix, 512 by 1024. Okay. All right, so this is the row wise sum. Now look, let's say we want to do the maximum. Same thing. We want to find the max value. Okay, like each we want to find the max of each row. So we'll be maxing across the column for each row. Similar concept. Instead of sum, we are just doing the max. Now, so it's the same thing, right? So you get the PID here, and this is, I'm just making sure that we don't get PID more than zero, more than m, because we launch kernel for each row we'll have we have a PID, right, because we are doing along the row. We get the PIDM and then the same offset along the end, right? So you do this, and then your base pointer will be your input pointer PID into stride, exactly similarly to what we did there. Here there's a small difference. You calculate because for max you need a minus infinity as your starting point. You cannot start with uh, like an zero, because that might be because for max, if you're randomly taking minus values also and you start from zero, that'll be a problem. So you start with a minus infinity because that's the minimum value you can have. So I start with an accumulator here. Same thing. You go across columns in block n chunks. So for I in 0 to n, this thing, you get the offset, you get the mask, and then I load it here. The other thing important here is you have to make sure that other is equal to minus infinity for the same reason, because we are doing maximum calculation. So you load the column values for that particular row, and then this is like, yeah, just to I had some issues with just, I mean, if your input is floating point 16, it's better to whatever your accumulator is, you should have the same sort of thing. So yeah, just to convert it into the same floating point number. If your input was floating point 16 or BP 16, this would have been problem. Just make sure. So I upcast it to float 32, and then I'm finding the maximum. Okay, so for each loop, you this is the running max. You take the initial max that you had, and then for these particular columns of block and columns, you get the max, and then now you get a new max, right? So you'll go on doing this till you get the max for that particular row, all the columns. What is the max, and then you store it out into an output pointer. This is exactly the same what we did earlier. Though I mean, this is very similar. The only difference is instead of doing sum there, you are doing max here, right? And this is TL max will take the you can do a maximum of two tensor input tensor. So accumulator is one tensor, and the other one is your max that you get from that particular block, right? And that's how you do. And then I'm just launching this using this. Okay. Yeah, and then I run it. You see that we get exactly zero. So here I've done the same thing using PyTorch, right? And then I'm doing the same thing using this is the Triton, and then printing out the error. And I see and then printing out the error here. I get exactly the same thing. And here again testing, make sure that actually my output and error are the same. Uh, okay, so. Uh, all right now, okay, this is how you do the max. Now I'll go move on to the softmax. So softmax is used widely in all the algorithms that have to do with LLMs and things like that. Let's see. So this is row-wise softmax. Same uh, sim simple concept, not very complex. What you do is first you find the max of each row. Uh, oh, sorry, of each row, and then you subtract that max just to make sure everything, when you do exponential, you don't have a problem. And then you do exponential of all the elements of all the columns for a particular row, and then you normalize it by the sum of that of all the columns for that row. So yeah, so exponential and divide. So max of all the max for a particular row, and you subtract the max from all the elements of that row, and then you do exponential, and then you divide the exponential by the sum of all the elements of that row. Okay, so it's like, yeah, max, subtract, exponential, and then normalization. Okay, so let's look at and I'm doing it row wise again. Same concepts. You have input and then output. You get the program ID. Your offsets are the same. You do 0 to block n, then uh, and here your output will be a two-dimensional, because this is not typically a reduction sort of algorithm. Your softmax, when you do of an input, there is no change in the dimensionality. So yeah, so you again have to calculate the offset for the output also. So this is the start of, you take X pointer and then your PID in by stridem. Similarly, what is the row of the output matrix? You calculate that. Now first, this is pass one. We calculate the max. Max is exactly the same thing. We take the max value, we do we do all of this, like what we did in the this thing in the previous max algorithm, and you get the max value from here. Now, because this is a single number, you need to broadcast it for all the columns, or basically all the blocks, right? So this is what I'm doing. I'm taking this max value and putting it in TL full in the block of n, right? Exactly. The reason is I need to subtract this max from each element in the column. Okay. So I take and broadcast it. The second part is finding the exponential. So I start with the sum value. I'm calculating the sum and the exponential both in this loop. So I do the same thing. I get the exponential. What is exponential? Whatever max value that I had here, I subtract it from each element and I do an exponential of that. Right. So this part. You for this part basically is exponential of in x, right? And this x is all the block, I mean each block of column that I load, and then I subtract the max from it and do the exponential. Okay. And then I need sum of all the numbers here, right? So I max value I got from here, but I need some, so I'm just doing some. This is the running sum I'm doing for each of these exponentials that I get. Okay. All right. Then I store, once I get these exponential, I need to store it in the output, and this that is where I take the output here, and then I store the exponential value here. Okay, and then once I have taken exponential, I need to normalize it with the sum value, right? So what I do is I go over all of these values exponential that I had. So again I load the from the output the exponential values, and then I normalize it with some value here, right? So I get the take the exponential, and then I divide it by some value which is going to be normalized, and this some value is coming, and this each kernel, the computation has happening for each row. So keep that in mind, right? This will be done for all the rows that you have, right? And just imagine that you have in parallel there are m rows, so all of these for each row. So this is row 1 0 1, row 0 row 1 all the way till row m. All of this will be done in parallel. Okay. And then yeah, once you get the input, then I'm just taking this and putting it back in the same place, but dividing it by the sum that we had computed here. Uh, okay, so like hopefully, so this the whole, so you again, right? So we calculate max here, the exponential and the sum for each row, and then you normalize it for for that particular row. Let's run it. Okay. Yeah, this is a softmax kernel. The input is going to be like this. Okay, so this is the input that is passed. So I take a random matrix X, and then uh, I call Triton softmax that I have here. Now, in Triton software, it takes input, then the block size is again optional. You can define it of whatever size. I just make sure that it's a two-dimensional matrix and then get the shape, rows and columns here. And the output also has to be of the same dimensionality. So I do out is equal to empty, like it has empty, like means it will have the same data type and also the same shape as the input tensor. Okay, so I get output, and grid is the same all the rows. So what this means is I'll have m parallel grid, right? M parallel programs running for each one for each row, and then I'm launching my softmax kernel with these values and then returning output. And then here I calculate return softmax and then the pytorch dot softmax, and then making sure that max error is as low as possible, so that it's like basically correct. All right, I run this, and you see it's almost equal to zero. Yeah, so this is how you like, some of this probably might be, just go through this and try to write it down on a paper and see if you have any issues, and if you face any issues, let me know in the comments. Thank you.